language. So the topic is cellulose, transparent wood, and nanostructured biocomposites. And Fredrik has given an excellent introduction to this topic. The first images here on the left-hand side, the image there is of a regular synthetic carbon fiber composite. So this is my background, the type of materials I used to work on. Then I came to KTH more than 15 years ago to take on the task of trying to do something with wood and cellulose. I think this image of cellulose, for instance, this is what I usually teach the students. It's a little bit misleading. If we only think about cellulose as a chemical entity, as a polymer with a certain repeat unit, we really miss out on one of the most important things, that it's a fibril with similar properties to Kevlar. And I think that's something we really should utilize to a larger extent. And actually, since I see that Anders Flodström is in the audience here, it's we seldom give credit to KTH, but when Anders was the president of KTH, he recruited a professor in wood science and technology who had very little experience in wood. And I think that was unusual at the time. And I think it was taking a big chance. And I took a big chance because together with Marielle, who is also sitting in the audience, who was the first PhD student, we put all the eggs in one basket and started working on nanocellulose. And so I'm very grateful to KTH for the opportunity to work on this. There was actually an organizational change as well. So the polymer department was combined with the pulp and paper technology department, which now, when you look back, is actually a very important strategic move from KTH. So, paper or plastic? So this poor person has, I don't think he cares very much about the choice, but I think it's an important one for us. Why is that? Well, I think it's obvious now that we as a society have a substantial problem with synthetic plastics. So since the 1950s, we've produced 8 billion tons of synthetic plastics. And out of those 8 billion tons, around 5 billion tons have been discarded. So it's either in nature or in deposit, but they're still there. And I think this is a gigantic experiment, and we don't know the consequences of that, because we're discovering that even the non-biodegradable polymers, they eventually degrade and they decompose into microparticles. And the consequences of those for our biological organisms are unknown. So we need to do something. And I think recycling is important, and I think biodegradation is important. So it's an excellent opportunity for cellulosic materials. So this is the work that we did together with RISE. So this is the work of Marielle from RISE. And the original idea comes from Gunnar Henriksson and Tom Lindström, using enzymatic pretreatment to disintegrate chemical pulp into nanofibrils. And now, this, which started out as an academic curiosity, is now experiencing an industrial breakthrough. We have companies in Japan, which I will come back to in a moment. In Northern Europe, we have Berglund and Stora Enso, and they are already producing nanocellulose at very large scale, and they have applications that are, let's say, very stable in a long-term perspective. And I think that these applications will lead to more high technology use of nanocellulose, because one of the opportunities we have is to make this large-scale nanotechnology. If you look at nanotechnology in other contexts, there is not so much that is carried out at large scale. One example where nanocellulose can be interesting is in the context of textile fibers. So now we are using cellulosic textile fibers of many different kinds, but one of the most important ones are fibers from regenerated cellulose. So you dissolve the chemical wood pulp with very high cellulose content, either using well, there are many different solvents that you can use. There are many activities on trying to use more environmentally friendly solvents, but you're still dissolving the cellulose. And I think that from a basic context, it would be much better if we could utilize the basic structure of cellulose, which we know has very high mechanical performance. So one project within the Wallenberg Wood Science Center, and I want to emphasize that this is not my work. This is work by Daniel Söderberg, Fredrik Lundell, and Lars Wallenberg. It's a very good example of multidisciplinary work. Lars Wallenberg's knowledge about colloids was combined with the fluid mechanics competence of Daniel and Fredrik. So they are preparing fibers based on these nanocellulose fibrils. So there is no solvent involved. So you can use a very green process and you can produce fibers that actually have better performance than the regenerated fibers today. Yes, I said I was going to comment on the Japanese effort. The interesting thing there is that they have a completely different outlook than companies in Europe. They are primarily interested in high technology applications. I think this is very interesting. They also have a very strong governmental effort where they want to make this their next carbon fiber technology. So they are not so interested in packaging materials. They are much more interested in high technology applications. And I think this will be interesting to follow in the future. And I have one example of their philosophy. We have a collaboration with the University of Tokyo. So basically, one thing that was really good when we started Wallenberg Wood Science Center is that we were able to take a much longer term perspective in our research. So not trying to solve problems in the immediate future, but to try to create opportunities for new technology. And this example, I think, is very nice in the context of nanotechnology. So basically, when you cast a film from nanocellulose, usually you think about high productivity, so you do it fast, and you end up with a structure that is not very well organized. You have your fibrils random in the plane. But what my colleagues in Tokyo did was that they let this take time. They did very slow solidification. And then you end up with liquid crystal order in your nanocellulose film. This normally only happens when you have rod-like cellulose nanocrystals, but these are fibrils, and they still show this liquid crystalline order. So in one case, when you do it slowly, you end up with some liquid crystalline organization. If you do it rapidly by filtration, you have a more random organization. Does it matter? Yes, it makes a big difference. And these are mechanical properties for these films. This is the random film, stress versus strain, the randomly organized film, the pneumatically ordered. And you see there is a substantial difference in mechanical properties. And if you look at the deformation pattern, it's much more inhomogeneous for the random film and more homogeneous and with a stiffer behavior. But this, of course, is difficult to industrialize at the moment because it's a very slow process. But it shows us the potential. If we can do this in a rational way, if we can find applications where this is makes sense, we can use this technology to further control the properties of the cellulose films. Basically, this is the preparation route that we're using. And I remember very clearly when we started talking about this that the paper industry were complaining, saying this will take too much time. You have a fibril that is binding too much water. It's just too slow. And maybe this is true, but I think that it's really up to industry to solve problems like this. And one advantage is, of course, that since you have a colloidal suspension, you can mix in other particles. And then when you dry the film, you have these particles distributed, and you don't need any binder. You use the intrinsic properties of the cellulose fibrils, and you bind a material that is solid and coherent. So one example is clay nanopaper. So this is from a project run by Lars, funded by SSF. So we mixed clay platelets, a very low-cost material, but these silicate platelets have excellent mechanical properties. So we're mixing this together. And if you look at the flame shielding properties, so this is a film which is only 100 micrometers in thickness. You put a torch on one side, and you end up with a temperature which is approaching 1000 degrees. And for 1 minute, the temperature on the other side, 100 micrometers, is below 200 degrees. So this is really remarkable. The explanation is thermal anisotropy because of the platelet organization. Cellulose has very unique properties when it's combined with clay. So it chars and forms an insulating layer. And also, the clay functions as a barrier to oxygen. So this slows down the burning process. It prevents volatiles from escaping and feeding the flame. So this is one example of how you can functionalize cellulosic materials by using the small-scale structure. Yes, so basically, what I've talked about so far is using the small-scale structure to build completely new combinations of materials. But as I said, there are also processing challenges. So if we could use fibers or even wood veneer, that has processing advantages because we can use the existing technologies. The applications that are already there, liquid packaging, viscosity control in inks, beauty products, liquid sorption, nanoporosity is used in filters, there are loudspeakers, and transparent barrier films that are based on nanocellulose. So this is the example of one of the most important applications. Stora Enso is making liquid packaging, and this is from their homepage. Light but strong cartons, and they're using microfibrillated cellulose, which is a relative of nanocellulose. We have not been involved at all in this development, but we have studied this problem. So if you look at the stress strain curve here for compressed paper, looks like this. For the nanocellulose film, it's much stiffer and stronger. But it turns out that if we add only 2% of nanocellulose, we can boost the mechanical performance of regular fiber networks substantially. And we understand the mechanism because the fibrils are binding the fibers together and improving the stress transfer between the fibers. So this is the mechanism. And if you understand the mechanism, you can optimize your material and you can improve the composition and the structure in order to further improve the performance. Another approach is to use nanostructured fibers, fiber materials, and wood. This is what Fredrik alluded to previously. So in other words, we start with a fiber, we try to preserve the structure, but we want to utilize the fibrils which are there, and we want to preserve them as much as possible to utilize their properties. So this is data that he already showed. You take oriented molded fibers and you polymerize, and you end up with exceptional properties. So compared with anything else, we are much above, both in terms of stiffness and strength. And It's a combination of several things, but one is that the intrinsic properties of the fibers are much better because we preserve them to a better extent. And the other thing is that we really know how to use the polymer now, because we have done all these careful experiments, so we are very, we make sure that the polymer is really impregnated at a very fine scale. I'll finish off with transparent wood, which is a recent project. It started out a long time ago when I visited my friend Hiroyuki Yano in Kyoto. For fun, out of curiosity, we made transparent crab shells. The applications are fairly limited, I think. We removed proteins, we removed calcium carbonate, so you end up with a chitin network. And to our amazement, when you impregnate this with acrylic monomers, you end up with a highly transparent material. So based on this, we had some understanding how this works, and we were thinking about how to do the same thing with wood, but we really could not come up with a solution. The basic problems are that there are chromophores in lignin that absorb light by themselves. There is light scattering taking place at interfaces between the cellulosic cell wall and the gas in the center, so we really need to address that. By coincidence, I was scanning the literature. I found an old paper from the early 90s. A wood anatomy professor had developed a technique to study wood species by optical microscopy, and he made transparent wood. So, but he never thought about the engineering perspective of this. So this is what we have worked on. So basically, we impregnate with the polymers, we remove the chromophores, and we end up with a highly transmitting material. And so now there are something like 10 people working on this, funded by the European Research Council. And we're doing all kinds of strange things. But the key is really that we're using a similar method as Fredrik was describing. So instead of having this cell wall with the cellulose fibrils, we create nanoscale porosity, which we can functionalize by different means. We can add dyes, we can add sonic particles, we can impregnate with polymers, and thus we can create completely new materials. And we've played around with this together with colleagues in Kista from a photonics group led by Sergei Popov. One application is we envision that you have load-bearing wood panels in the ceiling, and they are LED panels. So we use quantum dots for lighting. We have made electrochromic windows in collaboration with Georgia Tech, so you can regulate the light coming into the room. And we have made a wood laser. That seems completely crazy, but it actually is not. So we're using the waveguiding properties of the wood fibers, and it works really well. Of course, it does not work as well as silicon nanotechnology, but it's a very low-cost laser that actually can have some use. Most recently, Celine Montanari has been making, she's combined this with phase change materials. So in other words, your transparent wood panel will be able to absorb heat when it gets too hot and release heat when the temperature goes down. And the key is really to get the phase change material inside the cell wall. And I think this is the essence, that we are trying to do difficult things to control the distribution of our active additives. And I think this will provide us with new opportunities also in the future. So to summarize, cellulose has excellent mechanical properties. We should use that, and we need to preserve the fiber structure of cellulose. If we use the nanostructure, we can then add new functions. And whether we are going to use fibrils or utilize the nanostructure of wood or fibers, it will depend on the application. Thank you very much.
Thank you. Thank you very much, Lars, for a very interesting presentation. Now, I would like to ask you